In this video, I'm going to talk about magnetic flux. We just saw in the previous video that if the magnetic flux through a loop changes, a current will be induced. So what is magnetic flux? I like to think about a fan blowing air through a loop. This will help us understand magnetic flux. So if the fan is blowing air, then you can see that if the loop is in its vertical position here, then a lot of air will go through that loop. So think of that as a lot of flux going through that loop, a lot of air. But what happens if you tilt the loop, right? You can see that less air is going to flow through that loop. So the angle of the loop affects how much air goes through. If it's perfectly vertical, you've got a whole bunch of air. But as it's tilted, now you can see the air can only pass through this space here. So you're not getting as much air through the loop. So now consider a magnetic field going through a loop. The same thing happens. If the loop is tilted, then there's going to be less field passing through it. If this is the length b of this side of the loop, then only a size b cosine theta, only that part of the loop is what will get air going through it. This comes from looking at this angle theta over here, which is the same angle as this one over here. So if this loop here had a length of b, little b, which has nothing to do with the magnetic field, it's just the length of this side here, then you can see that this is the side that is adjacent to the angle, and so it's b cosine theta. So we like to call this the effective area. So the effective area of the loop is reduced when you are tilting that loop. So if the loop is perfectly vertical, you've got all this field here going through it. But now as you've tilted, it's as though you've made the area of this loop smaller now, because only this part of the loop is getting the air through it. So what you want to visualize when you're thinking about magnetic flux is how much field is going through that loop. The more field going through it, the more magnetic flux through that loop. We're now ready to define magnetic flux. Magnetic flux depends on how strong the field is and the effective area of the loop. You just multiply those two together. B is the field, A is the area of the loop, and that cosine term makes it so that we only get the field that is passing through that loop, as we saw in the previous slide. Capital Phi over here is the symbol for the magnetic flux. The units are the Weber. I hope I'm pronouncing that correctly. I do have a note here, which is that in this equation, theta is the angle between the magnetic field and the normal to the plane. This mimics what we saw in the previous slide, but basically we care about this angle theta, which is between this line here, which is the normal to the loop, right? The normal is a line that is perpendicular to this loop, and theta. So you can see that by doing cosine of theta, instead of thinking about we're looking at the effective area of the loop, you can also think about the fact that, well, cosine of theta is going to take the component of b that is along the direction of n. So that cosine theta is really giving us the component of the magnetic field that is perpendicular to our loop. I have a picture to help explain this because this is a lot to take in. So if we write down our definition of flux that we just saw in the previous slide, BA cosine theta. Here is the loop, here is side view. So the normal to the loop goes this way. So if theta is the angle between this normal and the magnetic field, which is these blue lines, you can see that theta is 0 in this case over here. If theta is 0, cosine of 0 is 1, which is why the flux becomes BA, because this crosses out to 1. So this means you get the maximum flux when theta is 0. But instead of thinking about, okay, does theta have to be 0 or 90? I can't remember. If you visualize the fan analogy, you can see that in this situation over here, all of the magnetic field lines are going through that loop. That tells you there is a lot of flux. So have that visualization that the magnetic field lines need to go through perpendicular to that loop. In the second picture over here, what we see is that the normal is up here or down, doesn't matter, but you can see that the normal is at a 90-degree angle to the magnetic field that was going to the right. So if you have your equation for magnetic flux, BA cosine theta, cosine of 90 degrees is 0, which means that the whole flux is 0. This should make sense because none of the magnetic field lines are passing through this loop. So no flux in this case, but maximum flux when the field lines go perpendicular to the loop. Let's do an example to finish up this section. It says that at a particular location, the Earth's magnetic field is 50 microteslas, tipped at an angle of 60 degrees below the horizontal. So I have a picture here that if you have a loop, you've got the field going down here, and 60 degrees below the horizontal is what is represented here, because this is the horizontal right here. So the angle with the field here, you can see, is 60 degrees below that horizontal line, below the positive x-axis. If we have a 10 centimeter diameter circular loop, what is the flux through that loop? So let's go ahead and define our givens. We are given the magnetic field, which is 50 microteslas, which is 50 times 10 to the negative 6 teslas. We know that we need the area of the loop. We are given the diameter. So the diameter is 10 centimeters. Let's convert that to meters. That's 0.1 meters. To find the area, which is pi r squared, we need the radius, which is half of the diameter. So that means that the radius is 0.05 meters. Now to find the area of the loop, we use pi r squared. So multiply pi times 0.05 squared, and we're going to get 0.0079 meters squared. So we have the magnetic field here, we have the area of the loop here. Now to find the magnetic flux, let's write down the equation. The magnetic flux is BA cosine theta, where theta is the angle between the normal to the plane of the loop, which is this vertical line here, that's the normal. We need the angle between the normal and the field, so that is what is given right here. 30 degrees is the angle between the normal and the field, not 60. So theta is 30 degrees. And now we can plug and chug our field, our area, and cosine of our angle. And when we do that, we get 3.4 times 10 to the negative 7 Weber. So just to summarize, keep in mind that we're trying to get a measure of how much field is passing through that loop. By taking this 30 degrees here and doing cosine of 30, we're getting the component of the field that is going vertical, the component of the field that is passing through that loop. So that's it for this video. Now that we know what the magnetic flux through a loop is, we can learn in the next video how we're going to change that flux, and then how that's going to tell us how much current will be induced in that loop once we change that flux. That's going to be Faraday's law.